welcome guys. Yeah, so this is my Sylow theorem 2 and then more results. So basically in this video, we will combine the first 3 Sylow theorem and get some further results that people usually talk in the Sylow theorem. And this result is just what I just collected. I'm collected a few years ago when I was an undergraduate. So share with you guys, and I hope you guys subscribe to my channel. Okay, so let me just quickly write down what we're gonna to prove, and I say that this is the Sylow theorem part 2. Okay, so let me just recall the first theorem. Okay, so Sylow has 1, 2, 3 theorem. Okay, so remember that our group G is P to N and N times M, and the greatest common divisor of PM is 1. And the Sylow group P group means that if you have a subgroup S, subgroup of G, which the order is just P to N, it's called a Sylow P. Okay. And in general, if you have another subgroup A, which is a subgroup of G, but A's order is prime power of something, then we call A is called a P subgroup. Okay, so let me just quickly write down the Sylow theorem that we just proved in the previous video. If you have not seen it, I will post a link below. So first theorem just tell you that Sylow P exists. Okay, so you need to fix a prime number. Okay, so Sylow P exists, and the second is that the Sylow P conjugate to each other. So this means that if you have Sylow H1 and H2 are both Sylow P, and then there exists group G element G such that G H1 G inverse is H2. Okay. And the third theorem tells you that the number of the Sylow group is called NP, just 1 mod M, sorry, 1 mod P, and NP divide M. Okay. M is this M. Okay, so this is the Sylow group, Sylow 3 theorem, and in this video we will prove the 4, 5, 6, 7. Okay, so 4, which also commonly used, is that so S, right? So now I write S as a Sylow P group. So if S is a Sylow P subset of G, so S is normal if S is the only Sylow group. So this theorem is is the simplest one. Okay. And so number 5 is that right. So we define a so-called normalizer. Right. So given any subgroup S, one can define a group G belongs to G such as GS. G inverse is S. This is called a normalizer of a subgroup. Okay, so what the 5 results, just the 5th result says that S is the only Sylow group of S. Right. So suppose you given me G and I give you S, which is a Sylow P group, I can construct a normalizer, and the Sylow group is the only this S is the only Sylow group of the normalizer. Okay. Okay, so number 6, 6 are 7 and 8. Yeah, so let's call it 6. So 6 is that so given any P subgroup, so let's say P is a P subgroup of G, then there exists a Sylow P S such that P is subgroup of S and the subgroup of G. Okay. Okay. And the number 7 is that if you have a subgroup, let's call it H, which covers some normalizer of the Sylow group. So suppose this H is a subgroup, right? And then it covers some normalizer of the Sylow P group. Then the normalizer of the H itself is just itself. Okay. So number 8, that's what we gonna to prove, is that is that suppose G is a P group, and then let's say H is a proper P subgroup. So H is indeed not the same as G. Okay, then the normalizer of H will definitely larger than H. Okay. So these 4, 5, 6, 7, 8 are like the generalization of somehow like the much more deep results. Not very deep, but then just some consequence of the first three. Okay, so once you have these all of these tools, then you should be able to do like the finisher. You should be solve most of your undergraduate group theory problem. Okay, so yeah, let's prove one by one. Okay. Yeah, so let's see. Yeah, so I think this one is a simple one. Okay, so let's prove this. So prove. So I proved that. So my theorem is that the Sylow S or the Sylow group is normal if this S is the unique only Sylow P. Okay, so you fix a P. So okay. So S is a subgroup of G. Okay, so obviously, so this proof is by 2, right? So the 2s tell you that any 2 Sylow P are conjugate. Okay, so now let's use this. Okay, so let's say S is normal, right? So if S is normal, and by this theorem that any 2 COP are conjugate, right? So you can let G as G inverse will give you all the Sylow group, right? But by definition, S is normal, so this will be S, right? So S is the only Sylow group. Okay. And also another direction, suppose S is the only Sylow group, then G inverse will be another Sylow group. But S is the only one, right? So this must be S. So S is normal. Okay, so you can obviously that this guy is just the second Sylow theorem. Okay, so it's somehow like exactly the same. Okay, so we just prove it. So number 5, see that S is the only Sylow group of normalizer of S, which is a subgroup of G. Okay, so I think, oh, by the way, this is normal. Okay, normal. Okay, so number 5. Well, number 5 is also trivial because so as we want to show that S is the only normal subgroup of N of S, or S is the only Sylow group. Because if it's only Sylow group, then it must be normal, right? So if I say S is a normal Sylow group of N of S, then sure, it must be normal. Okay, so also the proof is also easy by 2. So all the Sylow group are conjugate. So that means if I only focus on these, right? Then you pick any G belongs to N of S, then G inverse will be S, right? So which tell you that since all the Sylow groups are conjugate, right? So if you use S and you do conjugate, you will generate other Sylow groups. But every G in normalizer of S will normalize S, right? So S is the only Sylow group. It's the only Sylow subgroup, Sylow group of N of S. Okay. Now let's see the number 6. So this you see 4 and 5 are somehow like trivial, right? So the 6, 7, and 8 are a little bit difficult. So I would say these are the actual should be viewed as the Sylow theorem 4, 5, 6. So these two are just some lemma level of the second. Okay, so P is a subgroup of G, then it is a Sylow S such that this. Okay, so now this one is a little bit tough. Okay, so Number 6 is that if P is a subgroup, is a P group, which is a is a P subgroup, P group of G, then there is a Sylow S such that Sylow P group S such that P is the subgroup of S and then G. Okay, so the key is that how to find such S. Okay, so the proof is very constructive, right? So you start. I think you can. Let's see. Okay, so let's see. So let's consider a group. Consider this P act on all the Sylow say all the Sylow groups. Right? So omega is all the Sylow groups, all the Sylows. Okay, and this P is basically, let's say, if any element P here, I just map into let's say this subgroups S, I just map into P as P inverse. Okay. Okay, so wait. Maybe let me just use H, right? Because the small p, the capital P and the lowercase p are hard to distinguish. So that's how to distinguish. So let me use H. So this is H, this H. Okay. So this SS is a Sylow group, and this is a group action. Okay. And I know that the number of omega is NP, right? It's just basically 1 mod P. But this H, right? This H is a P group. So H is a P to a something. Let's say P to A or something. So this omega by a class equation, so this will be 1 mod P will be P to A divided by something, right? So divided by some conjugacy class, right? But since this is omega is not divisible by P, so there must be something which clearly cancel all the P, right? So there must be one so-called trivial orbit. Okay. So there is a trivial orbit. Now let's call this trivial orbit S, right? So there is a trivial orbit S. So such that right, so it's trivial means that H will fix S, right? So it means that H inverse is S, right? Which tells you that H become order for all H, right? So that means H is a subset of the normalizer of S. Okay, so from here, H is a subset of normalizer S, right? And we know that S is the normal S is also a subset of normalizer S. Okay, so here comes the theorem that I think I proved in the counting formula. So S is a normal subgroup of S is a normal subgroup of N of S, right? Because we just proved that the S is the only Sylow group, so it must be normal. So this is by the number 5. So by the group theory, the third group theory, group isomorphism theorem. So third iso tell you that SH is a subgroup, right? So it's a subgroup of N of S, right? And the SH is just S times H intersection this. Okay. So, but you see, if so now these were greater. So now S and H, right? So S is just P to N. Let's say H is P to I, right? And I will less or equal to N. So from here, that you guarantee that P N plus I divided by something. Okay. But this guy is the subgroup of this, right? Okay. So this SH is a Pn plus I divided by something, and this SH is can at most with prime power, right? Because this is just a prime power. But I know that I know that S is the largest prime power group, right? So this SH is another subgroup which is at most prime power, right? So from here you know that SH must be what? Must be S, right? As a number of the sets, right? So tell you that SH is another Sylow group. That I just showed by 5. I just showed that S is the only Sylow in normalizer of S. So which tell you that the SH must be S, right? So you tell that H is a subset of S. Okay, so H is a subgroup of S. Okay, so this is the theorem that we just proved. Okay, let's see. We just proved this. Okay, so let's go to number 7. So number 7 say I think it's an easy one. So let me just write down number 7. So number 7 says that if you have some subgroup H which contained some normalizer of the Sylow P, so that means we have this diagram, and we get n of H, which is G. If we have this, then n of H will be the normalizer of H will be self. Proof. Okay, so the proof is simple. Let's pick up. So the proof is just pick some A, right? A belongs to the normalizer of H. So A belongs to a normalizer of H, and we want to show that A belongs to H, right? So by definition, So by definition, A is this, right? So if we focus on this line, which tell you that S is the Sylow subgroup of NH. So S is a Sylow group of NH. Okay, so which tell you that if you use A as a inverse, will be another Sylow group, right? It's another Sylow group of N of H. Okay, so right. So A as inverse is another. Let's see. Right, so A as A inverse is another Sylow group of NH. Right, but let's see. So, but you see. So this if you focus on only this line, right? If you focus on this line, then you know that AH by definition, right? So A inverse will be H since it's normalizer, right? So that means A will normalize any element of H as a set, right? So actually A will fix A inverse for any H will give another set in H. So A as A inverse is another subgroup, not just N of H, but another Sylow subgroup of H. Okay, because this element in S is a subset of H, right? So that means also S is a Sylow subgroup of H. So which tell me that so I have S is a Sylow group of H, and A as A inverse is a Sylow group of H. So they are conjugate to each other by the second Sylow theorem, right? So there it is H belongs to H such that S is H as A inverse H inverse. So this S is just H A, yeah. So you can write as this. Right, so since they are conjugate to each other. Okay, so now you get what you get. HA belongs to N of S, right? Normalizer of S. But now here comes the magic because H contains the normalizer of S, right? So and then this is H belongs to H, right? So you get A belongs to what? A belongs to H because the left hand side this belongs to H and the right hand side this belongs to H. So you start from normalizer of H, but finally you prove that A belongs to H. So you get N of H is subset of H. So N of H is the same as H. Okay, so we prove most of them, right? So let's go to the final one. So final one says that if G is a P group, H is a proper P subgroup, and H is not the same as G, then none of H is not the same as H. Okay, so actually one can use this to prove that is equivalent to the following. I think it's the equivalent to the following says that if G is a P group, P subgroup, so H is a P subgroup of G, but H is not Sylow, okay, so H is not the largest, then the normalizer of H will greater than H. Okay. So you can easily see that this will imply this if you restrict it, if you just change this H into G. So you just restrict it to particular P subgroup, and which is not Sylow. And you use the theorem that we just proved that if H is a Sylow P, if H is a P subgroup, then it will contain in some Sylow group. So there will be another Sylow P, and then you use this S as this G, and then you can show these two are equivalent. Okay, so I only prove this, right? I think this one is a very interesting one. Okay, so number 8, if H is a, let's say H is a if G is a P group and H is a subgroup, well, definitely the P group means that G is something prime power, right? So H must be another prime power group, but it's proper. Then N of H will definitely larger than H. Okay, so the proof is very weird. It's a little bit weird. Is that I can consider H, right? I can G H. Okay, and the G quotient H is let's say I use a left coset, so the element should be written as XH. X belongs to G, and the group action defined to be H mapped to X on this set become so H X on this set XH just become HXH. Okay. Yeah, that's it. Okay, so what the set of, so let's say your P divides some G quotient H. P divides the order of G quotient H. The reason is that H is not a P, it's not a Sylow, it's a proper subgroup. So there will be remaining prime power P, which left, right? So but there is a orbit which is fixed, which is H, right? So you see that H is a trivial orbit, right? So H is a trivial orbit. H is a trivial orbit. The reason is that H will fix itself. But if you use a class equation, right? If you use a class equation, then you will get something. This is one. This is come from H plus other term, right? So other term will be some prime power because this H still contains some prime power over something. But this is divisible by P, and this guy is divisible by P. If there is no other trivial orbit, then you are left one, so contradiction. So the only case is that there exists another orbit, another trivial orbit. So here is a key step that there exists another trivial orbit that's called K. Okay, so K is not the same as H. There are different subgroup, and such that such that you can find H, which fix K, fix K. Okay, so K must be the form, let's say GH, right? So for G is not the same as G is not in H. Okay, so there exists as for all H belongs to H, we have HGH equals to GH. Okay, so which tell you that G inverse HG belongs to H. Okay, for all H, but this is the same as G inverse HG will be H because they are finite group. Oh, by the way, all the theorem I say in this video are all finite. Okay. So, but this G do not belong to H, but G normalize H, right? So which tell you that G is the in the normalizer of H. So which prove that the normalizer of H is strictly larger than H. Okay. Okay, so yeah, this is the theorem. I think all the theorem of the Sylow theorem that we just mentioned, and there's a generalization of the Sylow theorem called the Hall's theorem. Okay, you can check it in the finite group theory, more advanced one if you like to see it. Okay, I think that's enough for this Sylow theorem video. Hope you guys feel happy. Subscribe to my channel. Thanks.